Hello everyone, you're welcome to this channel once again. Today we have another question on how to calculate longitudinal displacement of a mass vibrating from the floor. Now let's read through the question. A kilogram person, that is unknown weight, illustrated in the figure below, is modeled as a timber with effective stiffness KEF 10 to 4 Newton per meter. The mass of the person is M person, which is 80 kilograms. If the person is standing on the floor vibrating at F equals 10 Hertz with amplitude of X of Y equals 0.01 meter, what are the maximum longitudinal displacement will the person feel, assuming that the initial condition are 0? Now today we are comparing or modeling a spring mass system of a timber to a person standing on the floor vibrating. So therefore, by modeling such structure together, we know that the person is standing on the floor vibrating with a frequency of 10 Hertz with the amplitude of Y equals 0.01 meter. Now we are asked to find the maximum longitudinal displacement. Now, how do we approach this particular equation? First of all, let's pull out all the parameters. We know the stiffness of the timber, which is 10 to 4 Newton per meter, and the mass of the person, which is 80 kilograms. We were given the vibrating frequency of the body standing on the floor, 10 Hertz. The amplitude displacement, 0.001 meter. Now that we were told that the floor is vibrating, therefore the damping ratio will be 0. So if the damping ratio is 0, using the equation of the XY displacement, amplitude equation of a mass body system on a resonance, which gives us this particular equation. Now that the damping ratio equals 0, that becomes xy, x over y equals to root of 1 over 1 minus r squared, which gives us this. Now that our equation eventually becomes this, we can now find the effective mass of the person. So by using the equation effective mass equals the given mass over 3, so that gives us 80 over 3, that gives us 26.7 kilograms. Now by slotting the effective mass and the effective stiffness into the natural frequency equation, which is Wn over KEF and MEF. So that gives us 10 to 4 to 26.7 root. That gives us 19.40 radian per second. Now that we calculated the Wn, which is the natural frequency of the whole body system, now we are to calculate the frequency ratio, which is R. Now to calculate frequency ratio, which is W over Wn, we have 10 to 2 pi of the vibrating frequency of the body, which is in Hertz. So it becomes 10 to 2 pi over 19.40, which gives us 3.2. So our frequency ratio becomes 3.2. Now that we have found the frequency ratio of the illustrated system, now by slotting all the values into the particular equation you were told, that becomes x over y equals 1 over 1 minus r squared. And knowing fully well that the displacement ought to be in millimeters. So therefore we multiply our y with 1000. So that becomes 0.001 multiplied by 1000 to multiply by the magnitude of the equivalent of the x displacement. This time around is in magnitude. So therefore, by slotting all our value, that is the frequency ratio r, into this particular equation, that gives us x equals 0.11 meter. Thank you very much.